Imagine this. You've written a digital filter. You've checked every loop, handled overflow, and verified the logic. You flash the microcontroller, feed a sine wave from a bench signal generator into the ADC input, and instead of a clean result, the FFT looks like garbage, a forest of unexpected spurs, and a noise floor that buries the result. Your first thought is always the same. I must have made a mistake in the math. So you start chasing your tail. You recalculate the filter coefficients. You change the data types from fixed point to floating point. You even start to doubt your own qualifications. But the error may be hiding in the one place you trusted the most, inside the test signal itself. And this is a classic manifestation of Finagle's third law.
In any collection of data, the number that looks absolutely correct and requires no checking whatsoever will invariably turn out to be the error.
Of course, if you have a high-end precision source on your bench, you can simply ignore this law. But what if you do not have one? I decided to attack the problem directly and design my own generator for a near-ideal signal. Part 1. Defining the target specs. For the hardware platform, we'll use an affordable development board with a Cyclone 4 FPGA on board. And before we start creating anything, let us figure out exactly what signal quality we actually require. Let's start with the device under test. In many modern microcontrollers, the built-in ADC is advertised as 12-bit. Typically, this is a successive approximation register converter, but nominal resolution and effective resolution are not the same thing. In practice, taking into account silicon noise and PCB layout, we usually get anywhere from 9 to 11 effective bits. Let us assume an optimistic case of 11 effective bits. Then, according to the standard ideal ADC formula, this gives us an SNR for the device under test of approximately 68 decibels. It is probably quite obvious that the signal generator must introduce less noise and distortion than the ADC being tested. To ensure our generator does not become the bottleneck during debugging, we'll add 30 decibels of margin. And believe me, that margin will matter later. Therefore, our target becomes 98 decibels. We will set the upper limit of the operating frequency range to 50 kHz. This means that in the frequency band from 0 to 50 kHz, the combined noise and spurious content of our generator must not exceed -98 decibels fs. The development board we selected for implementing this generator is equipped with a 50 MHz crystal oscillator. This will serve as the base clock frequency for our entire system. In this version of the project, we deliberately avoid the on-chip PLLs. Yes, we could push the FPGA clock higher, but for now, architectural simplicity, spectral predictability, and avoiding extra PLL jitter matter more. Let's calculate the oversampling ratio, or OSR. In this case, it is the modulator clock rate divided by twice the signal bandwidth. An OSR of 500 gives us a very comfortable margin, and this is exactly what gives us so much design headroom. An OSR this high lets us use aggressive noise shaping while leaving plenty of headroom for the digital filtering that comes later. And that is exactly what we are going to use next. The core block, how the delta sigma modulator works. So the parameters for our generator are clearly defined. The upper frequency of the operating range is 50 kHz. The required spectral purity is approximately -98 decibels fs. And the hardware platform is a Cyclone 4 FPGA. To generate an analog signal from digital data, we will use a delta sigma modulator. Let us first try implementing a first-order modulator and understand exactly how it works. In the previous episode, we clearly demonstrated that a traditional PWM creates powerful spectral components at the carrier frequency, its harmonics, and its sidebands. These high-energy components have to be heavily suppressed by an analog filter, and doing that is not always an easy task. A delta sigma modulator works very differently. It has memory and is controlled through a negative feedback loop. The core principle is actually embedded right in the name of the technology. During the first stage, the system calculates the difference, or delta, between the current input sample and the previous value of the 1-bit output, which is fed back through the loop. Then, crucially, the error is not thrown away. It is integrated in an accumulator. That accumulation is the sigma part. Finally, based entirely on this accumulated sum, the quantizer makes a 1-bit decision to output a logic 0 or logic 1. As a result, the 1-bit output continuously toggles between its extreme digital states. However, after averaging and low-pass filtering, the average pulse density follows the input waveform. In the frequency domain, the key effect shows up, The feedback loop, working in tandem with the integrator, actively shapes the spectrum of the quantization error. The quantization noise is actively pushed out of the useful low-frequency band and pushed up into the high-frequency region. That is noise shaping. In order for noise shaping to operate efficiently, the clock frequency of the 1-bit data stream has to be much higher than the minimum required sampling rate for our specific signal. That ratio is the OSR that we calculated just a moment ago. In our design, it is exactly equal to 500. Let's check the math and see what this number gives us in practice. The general formula for calculating the theoretical SNR for a modulator of order L looks exactly like this. If we substitute our value of 500 into the formula for a first-order modulator, we arrive at a theoretical performance limit of roughly 77 decibels. And that's the problem. Remember that our minimum target was 98 decibels. That tells us that a first-order architecture is not good enough for this application. So we need to move up in order. That means a second-order architecture with a second integrator in the feedback loop. A second-order modulator provides a massive 15 decibel improvement in the SNR with every single doubling of the sampling frequency. Let us recalculate the potential of this new circuit, but this time using the simplified formula specifically derived for a second-order system. And there it is. A second-order modulator running at our specified clock frequency is theoretically capable of delivering 123 decibels. This provides a very solid engineering margin, well above our original target of 98 decibels. Does that mean we're done? Not even close. Those 123 decibels represent a theoretical upper bound for an idealized mathematical model. In a physical device, that beautiful margin will immediately begin to be lost to clock oscillator jitter, power supply rail noise, limit cycles within the modulator itself, the finite bit depth of our digital arithmetic, the non-ideal characteristics of the output filter, and, of course, the output stage. Therefore, our next engineering task is not merely to draw a block diagram. We must rigorously verify exactly how much of this theoretical performance margin actually survives in a numerical simulation model. It is far better to analyze the realistic spectrum right now, in software, rather than endlessly searching for lost decibels later on the physical hardware. How do we do that? Exactly. We need to build a simulation model. Part 3. Modeling and verification of parameters. Theoretical calculations alone are only half the job. Real engineering starts with thorough verification. To validate our mathematical estimates, we have constructed a complete software model of the delta sigma modulator. Let us define the baseline parameters. The input data stream will have a resolution of 24 bits, and, for our test signal, we will generate a mathematically ideal sine wave. Yes, a pure sine wave creates somewhat idealized test conditions. However, at this specific stage of development, it is exactly what we need to clearly visualize the fundamental mechanics of the algorithm in action. For those who want to dig deeper, here are the implementation details. The program implements a classic second-order Boser-Wooley architecture. To avoid overflow and keep the loop stable, the input amplitude is limited to -6 decibels fs. To suppress idle tones, we also add digital dither. The spectrum is calculated using Welch's method with a Blackman-Harris window. The complete source code for this simulation model will be available for download, allowing you to run your own experiments. When the script finishes, we get a parameter summary and a comprehensive spectrum plot. Exactly as expected for a second-order modulator, we can clearly see the noise floor rising sharply in the high-frequency region. Its characteristic slope is very close to 40 decibels per decade. That's a clear visual confirmation that our second-order noise shaping is working as expected. Now, let us examine the critical numbers. The integrated in-band signal-to-noise and distortion ratio, or SNDR, measured from 0 to 50 kHz, comes out to 113.8 decibels. Consequently, the effective number of bits, or ENOB, reaches a solid 18.6 bits. You might immediately notice a slight discrepancy here. Why did we only achieve 113.8 decibels when our theoretical limit was calculated at nearly 124? That actually makes sense. First of all, we intentionally reduced the input amplitude to guarantee system stability, which immediately drops the theoretical ceiling to 117.8 decibels. Secondly, the digital dithering we deliberately introduced, along with the residual noise from the 24-bit quantization, both cost us a few decibels. However, even when we account for all of these inevitable real-world losses, a final figure of 113.8 decibels still provides us with a healthy performance margin over our initial design target of 98 decibels. Conclusion: the real fight for decibels is just beginning. We have achieved almost 114 decibels of clean dynamic range. We have a beautiful, clean spectrum graph and an architecture completely validated by our model. But we absolutely cannot let this make us complacent. We fully understand that, for now, these are merely software simulation numbers. The reality that awaits us when we actually transfer this mathematics into the FPGA fabric is going to be a brutal fight for absolutely every single decibel. Today, we successfully designed the core block of the system, the delta sigma modulator. But to turn this into a complete instrument, we are going to need several other critical blocks. We need to write the RTL code, and, of course, we need to design the analog section of the device. Essentially, this is a brief roadmap of exactly what we will be covering in our upcoming episodes. And that is exactly where the real engineering battle will begin. We will face truncation error, phase truncation, clock oscillator jitter, and power supply noise. Every single physical component will eat into that precious performance margin that we have worked so hard to build up today. Will we be able to preserve these decibels once we move to real hardware? We will find out together in the next episode. Please subscribe to the channel so you do not miss it. The true hardware engineering is only just getting started. I'll see you in the next one.